Okay. So yesterday lecture we have seen what are the theories of failure and why these theories of failure are required. Also we have seen how the complicated task is that how we are going to analyze the force. Also I think we have completed this or just we have to start this maximum principal stress, that is normal stress theory. So we'll start from this point, that is maximum shear stress theory. As per our discussion, yesterday's discussion, we have seen that various theories are there for the analyzing the failure in the material. Also, we have seen how the failure is going to come and how the stress are generated in any component, or how the forces, external forces are acting on that component, and hence the stress is generated in that component. So as the uh, complications are increased in analysis of that stress because of the complication which has increased in the force which has applied or which is coming on that component. Before that, once again, let me ask one question, that am I audible to everybody?
Yes, sir.
Okay. Is it fine? Voice modulation, or just I have to increase voice or decrease?
No, sir, it's okay.
It's okay. Okay. So that we have seen that stress is the main criteria which we are going to consider for the analysis. And stress is the product of force and cross-sectional area. That relationship we are knowing. So first of all, we'll see this is very simple as well as the first theory we can say, because simply when we are going to analyze the failure, at that time we are going to say that the stress which is increased in that component beyond its capacity, it is going to create failure. So what stress is going to increase? That stress we are going to consider as a principal or normal stress is increased. For example, if you are going to consider the tensile test, which you might have conducted on universal testing machine by keeping that test specimen in two jaws of that universal testing machine, and you goes on applying tensile load. At that time, the principal stress which is generated into that specimen, if it get exceed, then its yield strain. Here you can see that this yield strain is relative. This yield strength, if you are going to consider in tensile stress, and if that yield strength is going to increase beyond, or this principal stress is going to increase beyond this yield strength, then we are going to consider it as a failure. And that may be the case for the multi-axial loading. That is nothing but this multi-axial loading which is taking place, and simply we have conducted test for one dimension only. That is, force is applied in one direction, and at that time, if you are going to get this sigma y as yield stress, then that yield strength can be utilized, though you are going to apply force in multi-direction, that is in x and y plane or in z plane also. If you are going to apply stress, then this principal stress is going to become more than the yield strength. At that point we are going to consider as a failure. Getting me? This is very simple, what we can say, theory, and gives roughly idea about how the part may get failed, and where this theory is allowing us to use this yield stress as a what base for the designing, base for the calculation of dimensions in that component. And same way we are going to see for the other theories also. So what is this? This theory is based on failure in tension or in compression. There is nothing but in simple case, in simple tensile or compressive load or tensile or compressive stress, this component is going to get failed. Though it is going to get failed by the shear, or it is going to get failed by some other type of stresses. Then we are going to consider that failure is going to occur only by tension or compression, and ignores possibility of other failures like shearing. Therefore, this type of or this theory is not suitable for the ductile materials, because in case of ductile material we have seen by taking one example. If you are remembering, in yesterday's lecture we have taken one example in which this example where we have calculated the shear stress, induced shear stress, right? And whereas we have permitted this shear stress, that is 60 megapascal is permitted and generated is 95 megapascal. This is based on this principal stress theory or maximum principal stress theory. Okay, and we cannot use this for the for ductile materials, whereas this theory can be used for brittle materials, because they are going to get fail either in tension or compression. Normally, they are strong for the shear. Okay, but in tension and compression, this material get fail, brittle material get fail. Hence, it can be utilized for brittle materials. Okay, so we can that results, though we are going to not getting accurate, we cannot ignore this theory. We cannot say that this theory cannot be used for designing of any component. But just what we have to do is that we have to use it for proper material. We have to check the properties of that material, and then afterwards we have to decide which theory can be utilized. Now, as the simplicity is there in case of this theory, that's why this is easy to understand and easy to utilize also. That's why it has its own benefits. But in certain cases, like in ductile materials, it is going to give wrong results. Failure is going to occur before the stresses are going to reach to its maximum value. That's why we have to use it for the brittle material. Okay. Now, this is the graphical representation of this theory. What it indicates that failure is going to occur because of the SUT, that is ultimate stress. As already in first slide it has mentioned that this can be used for the brittle materials. That's why here we have used this SUT as a limit for the stress, that is ultimate stress. Okay, instead of taking yield stress, because yield stress is not the criteria for selecting of this particular failure. So we have used this SUT in this y direction, SUT in x direction. Now one can ask that why it is more, as if you are going to consider this as a stress axis in x direction and this as a stress axis in y direction. Then if you are going to say here SU2 limit is comparatively smaller than its negative value. What it indicates actually, it indicates that this is for the tensile one. We are given plus sign for the tensile stress, whereas for the compression we are given negative sign. And for any brittle material, we can say that capacity of sustaining compressive stress is higher than the capacity of sustaining tensile stress. That's why this graph, which has located here, is going to create this value SUT towards positive side smaller than the SUT towards negative side. This is the same case in case of force which has or stress which has generated in y-axis, right? So can be erased. So what we are going to say that this is the simple, what we can say, graphical representation of this theory. It means that in this square, if the stress is generated in that component, if suppose this value is 5 megapascal, this value is 10 megapascal, and suppose here that ultimate value is 250 megapascal. Okay, but it indicates that here also we'll say it is 250, and here we'll say it as a 350. Here also it is 350. Okay. If suppose these are the stress values, here we have mentioned as a 5, 10, likewise it will move up to the 250. Here also we can mention, and it will come to the 250. On negative side also we can mention that, and it will come to the 350. Towards on y-axis also we can mention it as a, it is increasing to the 350. Okay. So any stress which is generated, suppose here is the point where in y direction tensile stress which is generated is 70 megapascal, and compressive stress which is generated in x direction is suppose 70 megapascal. So whether this part will get failed, because multi-axial load is applied, y-axis tensile load, x-axis compressive load is applied. Okay, and what the stress are generated are compression stress which are generated is 70 megapascal, and tensile stress which are generated are the 70 megapascal, and point is lying here. We'll call it as the x point. So whether that part will get fail, anybody of you can unmute yourself and just you can give answer, or you can write your comment in message box whether it will get failed. Any one of you, please. Harshvardhan Ubale. Harshvardhan Ubale, please unmute yourself. Are you able to listen me? Harish Rai. Who is there? Abhijit. Are you able to listen me?
Yes, sir.
So then why this Ubale is not able to give
Yes, sir.
answer? Ubale. Harshvardhan Ubale. Are you there? Are you listening me?
Yes, sir. Yes.
So, simple
Yes, sir.
question is that whether that part will get fail if the stress which is generated are 70 megapascal tensile and 70 megapascal compressive in x direction and y direction, and point is lying where on at point x. Is it right that I have mentioned that point? Hello?
No, sir.
Where I have to mention then that point?
At center.
At center. Why? Because tensile load stress which is generated is 70 megapascal in y direction. Whether I have taken 70 megapascal in y direction?
No, sir.
This, suppose this thing is 70 megapascal, this thing on y axis. Is it right? And on x axis, this is also 70 megapascal compression. So where I have to mention compression? In negative side, am I right?
Yes, sir.
And where I have to mention tensile? On positive side. Am I right? Hello? Ubale.
Sir. Yes, sir.
So where that point will be then? whether it will be at X or it will be at some different point. Once again, I will explain it. हाँ बोलो हर्षवर्धन बोलो.
Yes, sir. I think it is correct, sir.
Think it is correct. Why you are thinking? It's just mathematics. Okay. So let me explain once again. Here हा जो y ऍक्सिस आहे हा स्ट्रेस आपण ह्याच्यावर लोकेट केलेत. हे जे लाल पॉईंट दिसत आहेत ते सगळे रेड पॉईंट जे आहेत ते स्ट्रेसच्या व्हॅल्यू मेन्शन करतात. आपण आज समजू की 250 मेगापास्कल वाय डायरेक्शनला टेन्साईल लोड आपलं मटेरियल सस्टेन करत आहे. 250 मेगापास्कल एक्स डायरेक्शनला आपलं मटेरियल सस्टेन करते आणि कॉम्प्रेशनला आपण निगेटिव्ह म्हटलंय. एक्सचं कॉम्प्रेशन आहे 350 मेगापास्कल, वायला कॉम्प्रेशन तेवढंच येऊ शकतं 350 मेगापास्कल. ओके. ह्या सगळ्या पॉइंटला धरून आपण काय केलं की एक स्क्वेअर ड्रॉ केला. आता काय केलं की एक टेस्ट स्पेसिमन आहे ज्याच्यावर फोर्स अप्लाय केलाय. त्यातला फोर्स आहे तो वाय डायरेक्शनला टेन्साईल फोर्स आहे 70 मेगापास्कल आणि एक्स डायरेक्शनचा फोर्स आहे कॉम्प्रेशन आणि तो आहे 70 मेगापास्कल. मल्टी ऍक्सिल आहे. आपण झेड डायरेक्शनचा विचार केलेला नाही, दोन डायरेक्शन मध्येच फोर्स अप्लाय केले. आता हे 70 मेगापास्कल पॉझिटिव्ह आणि 70 मेगापास्कल एक्स ऍक्सिस वरचा निगेटिव्ह, हे जे दोन फोर्स जे अप्लाय केले होते त्याच्यामुळे तयार झालेला जो स्ट्रेस आहे त्याला स्ट्रेसला आपण लोकेट करताना मग एक्स पॉईंट लोकेट केला पाहिजे. बिकॉज इट हॅज अ व्हॅल्यू ऑफ 70 मेगापास्कल टेन्साईल in y direction and 70 megapascal compression in x direction. Am I right? Yes. Then
Yes, sir. Yes.
right. So this design is safe according to the principal stress theory. We are allowing that 70 megapascal in y direction tensile force and we are allowing 70 megapascal compressive force in x direction. So this design is safe according to the principal stress theory. So any point which is lying in this square, that point is considered as a safe point. Any point which is lying and any stress we can generate which is lying in this square. So beyond this square, if the point is going, suppose what we are going to do is that we are going to consider, I'll change the color of this pointer. I don't know if it's possible or not. See, suppose we have applied load in x direction and y direction. So what we have done, we have applied some force in y direction so that it will generate 30 megapascal stress in y direction, this yellow point. But we goes on increasing the stress and we have increased it up to suppose 300 megapascal. So this point will be of 300. This is 250 and this point is of 300 suppose. Then it is crossing this ultimate tensile test or ultimate tensile stress. So whether this point which I have mentioned in yellow will give us safe design. Anybody of you? Whether it is allowed that in x direction we can apply a load in such a way that it will generate 300 megapascal stress. Harshal? Who can give answer? Rai?
No, sir.
It is not allowed, right? So that part will get failed. So we can say that any point which is lying beyond this square, that is going to not the safe stress level for that component. So simply we can just consider this square, and we can just say that all these things are lying in the square are safe, and remaining all beyond this square, beyond this limit, are unsafe, and hence we cannot go beyond this square. So this is what the simple principal stress theory says. Okay. Is it understood by everybody? We'll move further. Now we are going to say that maximum shear stress theory. As we come to know that the principal stress theory is going to get failed in case of shear stress, because in that case we are going to consider only tensile or compressive stresses are responsible for failure. No other stresses are generated in that, and the component will not get failed by any other type of stress. That is what the assumption is there for the principal stress theory. But in actual practice, we have seen that the parts are going to get failed because of the shear also. Though they are capable to sustain tensile force, though they are capable to sustain compressive force, then also beyond that limit or well below that limit, that part is going to get failed. And that later on, that analysis is done why the part has get failed. Then it comes to know that it is failing because of the shear. So what happens to the shear? That we are going to find. And in that case, this next theory comes into picture. That is the maximum shear stress theory. In this maximum shear stress theory, we are going to consider that the part is going to get failed because of the shear, not because of the tensile force, not because of the compressive force. It is going to get failed because of the shear force. Now, directly the shear force, which is may not be applied on that component. Directly, you are going to apply only tensile force, suppose. But then also, in case of ductile material, failure is occurring because of shear, not because of the tension, though you are applying tensile force. In that case, the shear stress is analyzed, and it has assumed that the part is going to get failed when shear stress is going beyond that the limit. Ultimately, it's given limit or ultimate limit. And that's why this theory is stated that shear stress. So this type of theory can be used for designing of shaft based on shear stress theory. Okay, and that is used for the ductile materials. Sorry. According to this theory, the failure of material will occur when maximum principal shear stress is maximum principal shear stress in material reaches to its maximum value. Okay, in simple tensile test. That is, again, we have not conducted shear stress test. We have conducted simple tensile test only. But that simple tensile test results we are going to implement for designing that component in shear also. Okay, forget about that all things. What we are going to do is that simply you are going to conduct test with the help of UTM, and you are going to apply tensile load, and you are going to get some results. Stress strain curve you are going to get. That stress strain curve you are going to use for this theory. Already I have told in yesterday's lecture that what are these theories? These theories are nothing but the available data, how we can implement for the given design. That is going to explain by this theory. And that mathematical formulas are given by these theories. Okay. Again, we are not going to emphasize on these theories. Just I am trying to make you understand these theories. Otherwise, in theory or in examination, that theories are not asked in details. Even you can simply write what happens in that theory, that is sufficient, because only theoretical questions will be asked in exam. But as we are going beyond that, we are going to design any component. At that time, one should understand what this theory is going to suggest. You should remember me while you are working in the company. And you should remember that, yes, if I am going to use ductile material, then which type of theory I have to use, and what this theory indicates. What is the significance of that theory? That's why we are going in details. Okay, let it be. So what happens if the maximum principal stress, shear stress, is calculated by means of maximum principal stress in one direction minus maximum principal stress in other direction, that we have seen in example, divided by 2. So this value we are going to get for the maximum shear stress, and this maximum shear stress in simple tensile test we are going to get as, because in one direction only you are going to apply force, that is sigma n divided by 2. And that's why if this will call as equation number 1, and second equation will call as equation number 2. If they get equate, this is equal sign. If they are going to get equal, that is nothing but maximum shear stress is going to reach to the allowable shear stress in simple tensile test, then that part is going to get taken. So this 2 will get cancelled, and we can get sigma 1 minus sigma 2 is equal to sigma n, where this sigma n is maximum normal stress in simple tension. That is nothing but the test which you have conduct on with the help of UTM. So this simple maximum normal stress is going to reach to this 2 principal stress, or you can say here values of 2 principal stress. Then the failure is going to occur. That is stated by this theory. That's all. Now, if you are going to represent it by the graphical method, then what it indicates? It indicates that here again we are going to say that this SUT is used because it is used for the brittle material. Now this SYT is used by because it is used for the ductile material. That is, you are going to consider yield strength here. Now in case of ductile material, yield strength in tension is equal to the yield strength in compression. That is there. But in case of brittle material, that somewhat higher value we are going to get in compression as compared to the tension. But here for the ductile material, we are going to get the same value. Now, case 1, in this case, if suppose we are going to apply only tensile load, okay, in both the direction, then failure occurs may not be because of shear, okay, or failure which is occurring as a more value. But when you are going to apply tensile and compressive, like in this example which we have taken, in this example, we have applied 100 megapascal in X direction as a tensile load and 90 megapascal in Y direction as a compressive load. So what result we are going to get here? Shear stress which are generated are higher, right? Because this minus sign is going to become plus if you are going to use compressive stress. If you are using plus sign for the tensile and minus sign for the compression, then this already minus sign which is there in formulae will become plus, and hence the stress value will get increased. Right? So here I have not drawn the square because its limit has going to decrease if one sign is positive and one sign is negative. This is negative sign and this is positive sign, and our formula says that sigma 1 minus, okay, if suppose this is sigma 1 and this is our sigma 2. So already sigma 2 has a minus value because it is compression, and our formula says that minus sigma 2. So what will happen? This minus minus will become plus. Hence this sigma 1 will get added in sigma 2. And that's why this region is not safe, more safe. Because the shear stress is reaching to the ultimate value easily because of this plus sign. But here it is not case. Here we can say this sigma 1 and suppose this is sigma 2. This is also plus. That's why it will become minus sigma 2. And the value which you are going to get, that value is so applied load. This is sigma 1 and sigma 2 is applied load. That is principal stresses which are generated because of the external applied load. And sigma n is the tensile stress which is generated because of the tensile test. Applied load, are you able to listen me?
Yes, sir. Yes, sir.
Okay. Applied load value is smaller. But in this case, this applied load value will get increased. And that's why it is reaching easily to this sigma n. Getting? And that is why it is not drawn as a square. It is coming as a hypotenuse of this triangle. Right? So what will be the shape region? This blue part will be the shape region where we can apply that stress. Where this part is our point, if it is coming within this area, that point we can consider as a shape point. And if it is exceeding beyond that, then we are going to consider it as an unsafe. That part will get fixed. Till now. If you have any question, please let me know. Hello? Hello? Anybody of you, please?
No question, sir.
Huh?
No question, sir. No question, sir.
Okay, you understood it.
Yes, sir.
Good. Then we'll move to the next. Okay. Failure may occur. Oh. Towards the maximum stress. Stress.